All right, so I have a distributed system or a network here of 32 nodes. Right, so what we're going to do is we're going to generate a private public key pair by using all of these nodes in a trustlessly. So how it works is each node will have their own share, which they generate, which is, we'll get into it. But what they do is they will encrypt their share and send it to every other node. Every other node will generate their share, encrypt it, and send it to every other node. And over a round-robin 5-step process, each node will do computations on the encrypted data that they receive from every other node in such a way that at the end of the process, we're able to generate a private key such that only the virtual machine is able to use the private key in an actual algorithmic or process. So each node will not know what the final private key is. They will only know that their public share that they generate. And there's extra security because we use a process called clear encryption, which is pretty much a way of generating an initial private public key, which represents each node's original share. And we can encrypt that data and do operations on the encrypted data such that when each node encrypts their data, sends it to someone else and gets back the data, they're able to decrypt it and get back the original data that they had. So that's how this multi-party computation works, is by doing computations on encrypted data. So yeah, let's see how this works. So if I go and start, this new keygen session is going to be round 1, where each node will generate their clear public key. When each node does that, you can see where we pretty much get our share, send to everyone else. Round 1 is us verifying that every other node has actually generated a share. You can see that commit, that's the verification. Then when this is done, round 3 is a message where we'll actually try and construct the private key. So we'll do more computations, send it to every other node. We send a direct message to each other node. Then they will verify it. So that's what's happening here in round 4. And then finally, in round 5, we will do a proof. And the proof pretty much is a way to verify that every node correctly done the right computations on their data and didn't try to send data and then change it for the next round. So yeah, and then at the end of the process, we will be able to generate the final key. It's slowing up loads because I shouldn't be doing this on my computer with 32 nodes. Jesus, that's big slow up. And boom, this is the proof at the end. It's a long proof. So this number here is the final proof. And if every node has the same version of this number, so you can see, yep, it's all the same, then we know we've generated the key correctly. And just to show you what the key looks like, this is the final key. So this is the secret key, and you can see that we generate from 2 large primes, but all of this is encrypted. All of this is encrypted data. And that means this is this key's share. The next one, if I go up to this one will be that key's share. So you can see his share is different. It begins with 9. This one begins with 1. And each node will have their own share. And if we want to use the key to sign data, we just send it off to everyone else to construct a full key. And that's how we do it. So that took 1 minute, 37 seconds.